Hello, I'm Zara, and today I'm going to review a paper. And the title is Field Irradiation of the First Batches Produced for the Chinese HTR 10. In this paper, um, we want to evaluate the HTR field performances by irradiation tests during normal condition at thousands degrees Celsius and during the accident condition at 1600 degrees Celsius. So the study of fuel performance by irradiation are carried out are carried out for four HDR10 spherical fuel element, and it was started in July 2000. The sample fuel element 5 and 7 are both from the first production batch. Meanwhile, the sample fuel element 8 and 12 are taken from the second batch. And we have the free uranium level of first batch and the second one are respectively 1.24 times 10 to the fourth and 2 times 2.23 times 10 to the fourth. Okay, this is a brief to the fuel element fabrication. The first thing, we have to prepare the uranium dioxide kernel through the modified gel precipitation, and then the pyrolytic carbon and silicon carbide coating layer will be formed through the CVD process in a fluidized bed. And the last one is the spherical fuel element will be formed through the quasi-isostatic process. And in this table one, we have the main characteristic of the fuel elements in the first two batches. And in this table, as we can see in this table, we have a bunch of information about each each coating layers and the kernels, like for example, the thickness and the density and etc. We'll move to the irradiation equipment. Here is the irradiation testing rig for HDR10 fuel, and this irradiation test was carried out in IVV2M reactor that is located uh, at Institute of Nuclear Materials, Russia. The IVV2M reactor is a prototype water-cooled and moderated that has thermal power of 15 megawatt and of thermal and fast neutron flux of these numbers. And the irradiation rig consists of 5 capsules. From top to the bottom will be named capsule 1, capsule 2, and so on. And each capsule will be controlled and monitored independently for the gaseous fission product release. The capsule 1 would be for loose coated fuel particle and 60 sample for graphite matrix. And sample 5, also sample 7 was in the capsule 2 and 5. Meanwhile, this sample 12 and 8 was in capsule 3 and 4. The irradiation temperature would be adjusted with by mixing ratio of helium gas and neon. Okay, so this irradiation test was carried out from July 2000 to February 2003, and with the irradiation temperature 1000 plus minus 5 degrees Celsius. And the burn of also the fast neutron fluence from each samples can be seen in this table. But however, there was an abnormal phenomenon that happened to the capsule 4 that consists of sample A. So the burnout can be could only be recorded to 37,000 megawatt days per ton mat- matrix. However, we did however the capsule board wasn't taken out from the reactor. During the irradiation test, the temperature of sample 12 in the capsule 3 was raised to the 1200 degrees Celsius for 200 hours when it reached the burn up of 38,000 of and 700 megawatt days per ton metrics and was and then raised to the 1250 degrees Celsius for uh 200 hours when the burnout reached 57,300 megawatt days per ton metrics. Uh, at the end of the in-pile test, the high temperature heating test was carried out for um, fuel element in a capsule 5 and was carried out in a reactor. We move to the results and discussion for a radiation test at 1000 degrees Celsius. As we can see from this figure of R2B to the burnout value, the R2B value of xenon did not increase significantly during the irradiation, but it fluctuated. The high R2B values here were due to the manufacturer defect, and we and the Burnley test was done to for fuel element from the first batch and the second batch, and from the first batch, we found that the defect particle are not the same from each fuel element, and the average free uranium level was 1.42 times 10 to the minus 4, and from the second batch it was 2.23 times 10 to the minus 4. So as mentioned before, there was an abnormal phenomenon that happened to the capsule 4, and here is the phenomenon. After 50 to 100 hours, the helium flow resistance increased, and after 5,240 hours, the tightness of space between fuel element and the internal metal box and graphite casing decreased, and also the gaseous fission product release was uh, raised from 10 to the 7th to 10 to the 3rd after 5,340 hours. The reading in temperature of the thermocouple was plummeted to the 560 to 600 degrees Celsius, and after that, term the temperature of the thermocouple was constant, and the measurement of the gases fission product release was stopped when it reached 5,980 hours. So this is the structure of capsule 4 in which the abnormal phenomenon happened. The fuel element will be placed here, and This is the thermocouple, and also this is the gap between the internal metal box and the graphite case um that in that gap the tightness decrease. So the failure that happened to the capsule core was suspected uh, due to chemical reaction between the graphite matrix of sample A with the impurities that flowed in through the helium flow, and that reaction released heat, and the heat uh, caused damage to the thermocouple and the graphite matrix itself, and as well as the internal metal box and the coated particle. And from that reaction, uh, the graphite matrix will form graphite powder that is hard to break, and that hinders the post-irradiation examination that uh, was carried out in a hot cell. And as we can expect that there was no intact particle found. To the results and discussion for in-pile heating at 1200 degrees Celsius and 1250 degrees Celsius. So 1200 degrees Celsius is the maximum temperature for the accident condition at HDR 10. And for the capsule 3, we raised the temperature to 1200 degrees Celsius and 1250 degrees Celsius for 200 hours each. And this increase in temperature would cause the gaseous fission product release to increase, so as well as the R2B value. But the R2B value would be back to the normal once the temperature was back to the normal. And uh, the post irradiation examination was done by disintegrating coated particle through the electrolysis principle. And here we have a note from DC power supply that is connected to the graphite matrix of field element. And here we have the platinum metal that acts as a cathode that would be inserted to the nitric acid solution. And from that, we obtain the loose coated fuel particles, and those particles would be examined by irradiated microspheric gamma analyzer or IMGA. So from the fact that cesium would escape more when the temperature test is high, we can use the ratio of uh, cesium isotope activity to the cerium activity to detect failed coated particles. And a field particle can be, say, a failed coated particle when the ratio of the volatile to the non-volatile fission product is less than this value, with a mean is the average activity of the particles of interest, and sigma is the standard deviation. So from the total of 2014 particles, we pick some random particles from sample 12 that have been disintegrated, and there is one failed coated particle found. And from the ceramic parts of 200 to 400 coated particle were inserted to the hot cell with the grinding and polishing machine, uh, and it would be observed with the optical microscopy. And uh, in this figure we can see that the cut that the silicon carbide and pyrolytic carbon layer layers are still intact. There is no fracture or defect from the irradiation, and also there is no corrosion on the silicon carbide, and the buffer layer had enough thickness, and there is no damage to the inner pyrolytic carbon layer. Move to the results and discussion for in-parallel heating at 1600 degrees Celsius. Actually, this test cannot be done like the prior test because there is no furnace for the 1600 test. So we have to um, increase the thermal neutron flux by moving uh, the capsule 5 to the center region of reactor core. Meanwhile, the other capsules was moved to the upper region of reactor core that has less thermal neutron flux, so the temperature cannot be reaching 1600 degrees Celsius. And we installed a thermocouple at the free fuel zone at the sample 7 in the capsule 5, but it underwent a damage, so the actual temperature must be calculated. So this is how the test was done, and after we moved the sample 7 to the central region of the core, uh, reactor core, we moved up the rig by 90 millimeters, and the reactor power would be increased gradually for 30 minutes until it reached its maximum power. And this test was done for 50 hours, and the test at the 1570 degree Celsius was done for 4 hours. This is the result for the release of gas fission product from S sample 7 in capsule 5, and from 2189 particles. There were 127 particles that failed, and the failure fraction was 60%. It is suspected that the fuel temperature in the capsule 5 was actually higher than 1600 degrees Celsius. That's why the thermocouple was damaged, and the actual temperature must be calculated, but the calculation depends on many things like the neutron and gamma heating powers, the geometry changes, and the performance of irradiated material, and so on. And these were the observation results for the ceramic parts of 200 to 400 particles. And as we can see that there were many defects in pyrolytic carbon and silicon carbide layers of sample 7 after the in-pile heating test. It can be concluded that uh, the defects on the coating layers were due to the thermal stress because the temperature is too high, but there is no kernel migration observed. But we can observe from this figure that there were many micropores observed in the kernel after the irradiation test was carried out. So that's all for me. Thank you.